In this video, we are going to be talking about the physical properties of aldehydes and ketones, meaning we're going to be talking about the solubility, melting point and boiling point trends, and of course the intermolecular forces that influence those properties. So let's start off by talking about the structure of this ketone functional group, or the aldehyde functional group, or any carbonyl functional group for that matter. This carbon here has a total of 1, 2, 3 electron groups around it. That means that this molecular geometry here is trigonal planar. That means that this is a flat. All of these atoms are in one plane. With this carbon bonded to this oxygen, we have to remember the oxygen is very stingy about pulling electrons towards it. So this little delta here means that this oxygen here will be partially negative, pulling electrons away from this carbon. So we do have a dipole here. This molecule is polar. So all of our carbonyl functional groups are going to be polar in nature. So now let's think about our functional groups. So if we have two aldehyde functional groups next to each other, so these are different molecules of aldehydes, we ask the question, can aldehydes hydrogen bond to one another? Can this molecule form a hydrogen bond to this molecule? Well, the answer is no. We do not have a donor. No H bonded to N, O, or F. The only H here is bonded to a C. And so the hydrogens here are not eligible for hydrogen bonding. And so there is no donor. Can ketone molecules hydrogen bond to one another? Let me draw up a couple ketone molecules. While you're thinking about that. So here's two ketone molecules. Can ketone molecules form hydrogen bonds between two hydrogens? We're going to say no for the same reason. No donor. There is no hydrogen bonded to NO or F in either of these molecules. So no donor in either case. We are polar though, and so there will be dipole-dipole forces, and of course all molecules have dispersion forces. But aldehydes cannot donate a hydrogen bond. Ketones cannot donate a hydrogen bond. And so there is no hydrogen bonding between two aldehydes, no hydrogen bonding between an aldehyde and a ketone, because you need to have both a donor and an acceptor to form hydrogen bonds. So now that we're thinking about our hydrogen bonding and our polarity, we can ask the question, with respect to hydrocarbons like our alkanes, just our plain alkanes, alkenes, etc., alkynes, would our aldehydes and ketones have higher or lower melting points than our hydrocarbons? Our aldehydes and ketones are going to have higher melting points and higher boiling points than our hydrocarbons, because our aldehydes and ketones, so that's our claim, And our evidence is that they are polar functional groups. And that our hydrocarbons are nonpolar. Since those are going to be nonpolar, they're going to be dispersion forces only. And since these are polar, they're going to have dipole-dipole. And then our reasoning is that dipole-dipole is stronger than dispersion and takes more energy to melt or boil. So we'd have to go to an even higher temperature to boil because the intermolecular forces are stronger. Now let's think about our aldehydes and ketones versus alcohols. Our alcohols are going to have the higher melting point and boiling point. So our aldehydes and ketones are expected to have a lower melting point and boiling point. And so we can use similar logic our aldehydes and ketones can't form hydrogen bonds. Alcohols can. And so our hydrogen bonds are stronger and require more energy to break. And so the alcohol will be higher. So here's a trend. So this is a whole bunch of different molecules here. You can see we have an ether, we have an alkane, we have an aldehyde, we have a ketone, and we have an alcohol. So we can see the trend here, and you'll see that the diethyl ether and the pentane are fairly similar in their melting point and boiling point, and with the bulkiness of the two carbons on either side, the bent nature of this, it's just not enough to cut it and make it a little bit higher. But these ones are definitely polar, and then this is the hydrogen bonding. And so the hydrogen bonding is outranking this dipole-dipole. And technically this ether is polar, but it's just the side chains are kind of hindering the ability for that molecule to exhibit its dipole. This carbonyl functional groups have a stronger dipole moment than the ether. I'm just going to write weaker dipole. So these trends in intermolecular forces do help us make predictions, and there's a lot of factors to consider, but most of the time it works out. And so let's make predictions about the relative boiling point of all of these molecules. So in each pair, select the one that you think would have the higher boiling point. Be prepared to justify your answer using that claim, evidence, reasoning strategy. Go ahead and pause the video and try to come up with everything, and then unpause the video when you're ready to compare your answer to my answer. Okay, so for a higher boiling point, we're looking for stronger intermolecular forces. So for this one, we have an alcohol, which is capable of hydrogen bonding. Because if we had a second alcohol molecule, this one can be a donor, this one can be an acceptor, and so this alcohol can hydrogen bond. So that's going to be a higher melting point and boiling point compared to this alkane. This one is just dispersion. Here we have a ketone versus an alkane. This is going to have dipole-dipole as its strongest intermolecular force between similar molecules. This alkane is just going to be dispersion forces between similar molecules. And so dipole-dipole is stronger. And so this one's going to have the higher boiling point. For this one, we have our alcohol versus an ether. Alcohols have hydrogen bonding. Ethers are bent, and so they do have dipole moments. And so its strongest intermolecular force is dipole-dipole. And so hydrogen bonding is stronger, and so that molecule is going to have the higher boiling point. Now when we talk about solubility, we have to think about our aldehyde or our ketone with water. Can we form hydrogen bonds with water? So we couldn't form hydrogen bonds with between two aldehyde molecules because we didn't have a donor. But water can act as a donor because it has that hydrogen here. And now we can see that we have these lone pairs here that act as an acceptor. And so we can form hydrogen bonds in between. So we can form hydrogen bonds between aldehydes and water. In a similar fashion, we can form hydrogen bonds between ketone molecules and water. So let me draw that up. So remember, our acceptor has lone pairs. And then our donor has H bonded to NO or F. That's an O. Acceptors are lone pairs. And that's a donor. So for the same reason, we can form hydrogen bonds with water. Now that we have a donor and we have an acceptor, we can form hydrogen bonds. Yes. There are limits to solubility. So if carbon chain becomes too long, they'll become insoluble. But for short chain aldehydes and ketones, they will be soluble in water because they can't hydrogen bond. Just because if your carbon chain becomes too long, then that nonpolar dispersion only part of your molecule becomes too big for the water molecule to interact with it effectively. So in your book, they talk about 4 carbons or less is soluble, and then it starts to decrease as the number of carbons increases in your molecule.